Hello everybody, welcome to my talk. In this presentation I will introduce uh, a new testing method, bending test fatigue test method for strip steels at 20 kHz. Strip steels also used for... Alright. Strip steels, also called flapper valve steels, used for compressor valves. As you can see, they come in different thicknesses. The ones that we are testing in our lab have the thicknesses in the range between 0.1 and 0.6 millimeters. Although the presentation today will only include one thickness, the one that we started with. So the goal of this work is to develop a fatigue test method for thin, high-strength strip steels at 20 kHz for very high cycle fatigue in the gigacycle regime. And to do that, it's best to use the ultrasonic fatigue testing system. Then we can reach these lifetimes within reasonable times. So the idea was first seen on a brochure by Shimatsu, the company, where they showed a similar setup. They have the horn, a 20 kHz horn. I have a laser here, yes, the 20 kHz horn, and where they clamped a strip steel specimen just below the horn right here. We took this idea further and we further developed it, and we designed our own specimen. We included a waist into the specimen, inspired by previous testing on strip steels at lower frequencies. The thickness of the material is 0.381 millimeters, and that is the thickness that will be included in this presentation. The bending of the specimen, as you can see in the top image here, it's expected to bend in the second mode, flexural bending. So it sticks out here and it flaps. The next picture will show you a better image. So this is a 3D CAD model of the setup. Over there you can see a close-up of the specimen sticking out like a cantilever specimen. We have the applied displacement in the horn right here, and that is and will be called U0 throughout this presentation, which is what we control during the experiment. We control the displacement right here. And then we will have a flapping specimen. We will also try to measure, or we have measured, the displacement of the specimen along this specimen with a laser sensor to try to confirm the calculations and the predictions. We used that setup that I just showed you to actually conduct experiments. We had different materials that we tested using that setup, and we did produce a couple of S-turn curves for different materials. Right here you see only one example from one material. My colleague will show you much more materials, S-turn curves from different materials tomorrow during her talk, together with Feiner analysis and all that part. Today we will not talk too much about the experiments, but rather on the development of the method, of the test method. But this is just to show you that we did actually get fatigue data from this setup. We got correct fracture in the position where it is expected to fracture, in the middle of the waist. And the fractography showed correct fatigue fracture as well. It showed evidence of plane bending and all the features that you would expect in a fatigue fracture. So it looks like it works perfectly. However, the S-turn curve here, as some of you probably noticed, it doesn't include stresses, but rather includes the displacements. And that is because we don't know the stresses in this specimen yet. We are still trying to investigate that. And we do that, of course, by FEM modeling. and this is what I will start talking about now. So we start with trying to design the specimen to find the right dimensions for the specimen in order for it to have a 20 kHz frequency. So this is actually what we started with, and we found these dimensions for frequency that is within the range. And then we ordered specimens with this geometry, and we tested it, and we got all the results that you saw before. However, after the testing was done, we did realize that this simulation is actually wrong. You see the end here to the right is the end that is supposed to be clamped into the horn, or between the horn and the rod, and therefore it shouldn't have any angle there. It should be straight out. So the boundary condition in this simulation was wrong and wasn't realized until after the testing. We fixed that with the right boundary conditions, and then we realized that the actual frequency of the specimen is 25 kHz rather than 20. And yet it worked. We did produce fatigue data without knowing the stresses. So how is that possible? For you who are used to use the ultrasonic fatigue testing system, you should know that every part of the system has to have an individual resonance frequency at 20 kHz, but this specimen does not, and it works anyway. And that is explained by the fact that the specimen has a mass so little compared to the rest of the system, so that the frequency of the specimen does not affect this frequency of the whole system. And the specimen is so small, so it's forced to follow the system, even though it's outside of its own resonance. So that was good. Lucky but good. Then we did the steady state analysis to try to calculate the stresses in this specimen. Applied a displacement of 5 micrometer where the horn should be, and we fixed the displacement in the transverse direction to correlate to the real life experiments. And we did that at a range of frequencies from 50 kHz up to 35, and we could see that the peak is at 25 kHz, exactly the frequency of the specimen that I showed you in the previous slide. But anyway, the test will be run at 20 kHz, and this is the value that should be the realistic value, 9.4 micrometer. This is the displacement of the yellow point here in the middle of the specimen. So at 20 kHz, we should expect 9.4, approximately double the U0. If you look at the stresses, we should expect something close to 70 megapascal at 20 kHz in the same point. And at 20 kHz, this is the shape of the specimen according to the FEO model. It's back and forth, so this end is where the horn is clamped, and you see there's zero angle going out from the horn, as it should be. Then we modeled the whole setup with the horn and the rod below the specimen to see the effects of that. We did a model analysis, and we found out that the frequency is well within the ranges, but again, as I mentioned earlier, the system here will be at resonance, but not the specimen. The specimen will be forced to follow the system. Here's the laser measurement that we did of the amplitude of the specimen along the specimen. Up to the right, you see how the signal looks like, and doing fast Fourier transform analysis reveals the frequency of the signal, which is 20 kHz. That is correct, measured experimentally. The sampling rate is 200 kHz from the laser, and the results were not as good as we hoped for. We have huge, large discrepancies between the FEM model and the measured displacement with the laser using the first setup. We do not know exactly why this discrepancy exists. We have some ideas. It's still under investigation. We have a couple of ideas on where to look. We think that other modes might come in and superimpose the amplitude and increase it in that way. We're not sure on which mode. There are several candidates, several modes that are close to 20 kHz. That could be a reason for that. We will continue to investigate it. But as of right now, we do not know the reason for this difference here. Anyway, at that time, we also came up with a new idea about a new test setup where we did get rid of the horn in the bottom. And what we did is we tucked the specimen into the horn instead. So we have one wavelength here with this small specimen tucked in here. And because it's so small, it's okay. It works. And it's much better system. It includes less parts, less problems, and it should be smoother to use. Model analysis shows a correct frequency and the same as before. The horn is at resonance, the specimen is not, it follows. And with this new setup, all of a sudden we get a very good agreement with the FEM model. So we do not get the discrepancies that we saw earlier from the first setup. That means that these modes that we think are coming in are not coming in when using the new horn. When using the new horn, the displacement amplitude is according to FEM model. Anyhow, we did do a lot of testing using the old setup, and we have a lot of results. So we would like to somehow estimate the stresses to be able to use these results. This is what we did. We made an estimation of these stresses in that specimen in the first setup. And also we will retest the same materials using the new setup where we know the stresses now. And after that, we will be able to compare the new and old S-ing curve to see how reasonable the values are. Anyhow, the estimate of the stresses, how that were done, if I just go back maybe. From the laser measurement, we could see that the relationship between U0, which is the displacement at the horn, and the displacement in the middle of the specimen is approximately 1 to 8. For every 1 micrometer at the beginning, we will get approximately 8 micrometer displacement in the middle of the displacement of the specimen. So that is the first rule, that we will use for the estimation. 1 micrometer in U0 will correspond to 8 micrometer displacement in the middle. And from abacus simulation, we could see that 1 micrometer of displacement in the middle corresponds to 7.45 megapascal stresses in the same point, same region. And then finally, we can finalize our assumption, very simple assumption, that 1 micrometer in U0 will correspond to 59.6 megapascal in the middle of the specimen. And we can use that number to replace this displacement on the y-axis to stresses. And then just do a fast comparison to old data from the same material at lower frequencies, we can see that these values are actually reasonable. Anyhow, we will, as I said, we will retest the material with the new specimen. We will be able to compare it to these old values. So a method was successfully developed for testing strip steels, and it was successfully improved to get rid of discrepancies. And the new horn was actually tested with a few specimens, and it was successfully, the specimens were successfully failed in fatigue failure. Thank you for your attention.